Hello there, and welcome to the Sleepless Scientist, a quiet corner of the universe where curiosity rests easy, and the vastness of space becomes something soft enough to dream about. Tonight, our journey will lead us into one of the strangest and most beautiful mysteries ever known, the black hole. Not just the void itself, but the glowing storm that circles its edge, where light bends, time stretches, and reality begins to blur. We'll linger near its horizon, listen to the silence it creates, and wonder gently what might wait beyond a place where even light forgets how to return. But before we begin, I'd love if you could take a moment to like this video and subscribe. Only if these calm explorations bring you peace. And when you're ready, leave a quiet note in the comments. Tell me where you're listening from and what time it is for you right now. It's always a quiet joy to see this constellation of night thinkers gathered from every corner of the world, each of us drifting together through time in our own way. Now, settle in, dim the lights. Let the hum of your room or the soft rhythm of your breathing be your companion. And if your thoughts begin to wander, let them. That's what they're meant to do. We'll still be right here, waiting at the edge of gravity's silence as we begin our journey into the calm, dark heart of a black hole. So let's start not with science, not with math, and not with fear, but with feeling. Imagine the night sky above you, not the one from the city, where lights blur the stars. No, imagine the deep country night, far from cars, far from noise, the kind of darkness that feels velvet and endless, stretching in all directions, dotted with scattered constellations. A sky that looks like it remembers things, millions of years of silence and motion and light. Now, picture yourself lying under that sky, feeling the earth beneath your back and the soft pull of gravity keeping you grounded. Out there, somewhere far beyond what your eyes can see, hidden behind curtains of light and distance, are objects that absorb everything. Not because they want to, but because space, time, and light itself cannot resist them. These are black holes, but perhaps hole is the wrong word. A hole sounds like something you could climb into and out of, something with a bottom. But a black hole is more like the idea of falling, frozen in time. It's not a place exactly. It's a region, one shaped by gravity so powerful that nothing, not even light, can leave once it crosses a certain invisible boundary. That boundary is called the event horizon, the point of no return. But we'll get to that. First, it's worth saying this. Black holes are not monsters. They do not roam through the galaxy devouring planets like a hungry beast. They're quiet, still, mathematical, yes, but also oddly poetic. They sit at the crossroads of reality and mystery, the edge of what we know and what we cannot yet know. And though they might sound like science fiction, they are deeply real. We know this because we've seen them, or rather, we've seen their shadows. In 2019, the Event Horizon Telescope gave us the first image of a black hole. Not the black hole itself, of course. We can't photograph what emits no light, but the glow of hot gas spiraling around it. A ring of fire around a perfect silence. That darkness at the centre wasn't empty. It was full of gravity, mass, time, and mystery. And yet, for all their strangeness, black holes are also incredibly elegant. They follow the same rules of physics that everything else does, just pushed to the limit. They come from stars. They are born in explosions. They spin, they grow, they even collide. Some sit quietly at the centres of galaxies like massive sleeping hearts. Others drift through space like ancient ghosts. But all of them bend the very structure of the universe. It's a little like listening to music with one note missing, a silence so deep that it defines the sound around it. That's what a black hole is. Not chaos, but calm. Not violence, but inevitability. You might wonder what it would feel like to fall into one, whether you'd notice, whether time would slow or stretch or stop, whether there might be something waiting on the other side, a mirror universe, a rebirth, a doorway carved into the fabric of space. That's the path we'll be taking tonight, slowly, carefully, wonderingly. We'll explore what happens when stars die and leave behind something denser than comprehension. We'll meet the different types of black holes, from small stellar remnants to supermassive giants anchoring entire galaxies. We'll drift slowly toward the edge, where time itself begins to behave differently. And eventually we'll fall in, not in fear, but in fascination. We'll explore the strange math that tries to describe what lies beyond the singularity, and the stranger still questions about whether anything, information, particles, even entire universes, might come back out again. This isn't a journey of danger, it's a journey of curiosity, like standing at the edge of a cliff and staring into the mist. Not because you want to jump, but because you want to know what's beneath the fog, and maybe, just maybe, to understand something about your own place in the cosmos. Because black holes aren't just out there, they're also ideas. They're about boundaries, between light and dark, between the known and the unknowable, between past and future. They are the quiet reminders that even the universe has its secrets, and that sometimes not knowing is part of the wonder. So as we begin tonight, I invite you not to worry about understanding everything right away. Let the words wash over you, let the questions linger, let the metaphors soften the math. You don't need a degree in astrophysics to marvel at gravity, or to feel small in the best possible way. And if you drift off before we reach the end, that's more than okay. The black hole will still be here, silent, steady, mysterious, just like always. Now take a breath, let the darkness settle in, and let's begin our fall into the most peaceful, most puzzling shadow in the universe. Let's begin, not with a fall, but with a fold. Imagine you have a thick woolen blanket laid across your bed, soft, heavy, and creased slightly with the weight of its own weave. Now imagine placing something small and dense in the centre of that blanket. A marble, perhaps. It doesn't simply sit on the surface, it presses into it. The fabric bends, not just beneath the marble, but all around it. If the marble were heavier, or the fabric thinner, the indentation would deepen. Now imagine the marble growing heavier and heavier, until it doesn't just make a dent, but begins to pull the very fabric inward, folding it, curling it, stretching it toward a point where the blanket no longer exists in the same way. That is the beginning of what we call a black hole, and yet, despite the name, it is not a hole. Not like the ones we dig in dirt, or the ones we peer into from the edge of a well. A black hole is not an empty thing. It's not a hollow or a void, but rather the most full something can be. So full of mass, so dense, that it no longer behaves like matter at all. It's a place where gravity doesn't merely tug, it devours. But even that sounds more violent than it needs to, because the birth of a black hole is not always an explosion or a cosmic war cry. Sometimes it's more like a quiet surrender. Let's drift back in time to the life of a massive star. Not the kind of star like our sun, bright, cheerful and steady, but one much larger, 10 times the mass, 20 times, 30. These are the overachievers of the stellar world, burning through their fuel in just a few million years. They shine fiercely, sometimes beautifully unstable, creating elements in their cores through fusion, iron, oxygen, silicon, building the periodic table in fire. But eventually their fuel runs out. The pressure that once pushed outward, balancing gravity's inward pull, begins to fail. And in that silence, gravity finally wins. The star collapses. And I don't mean it deflates gently. I mean it folds inward at a rate so fast and so complete that the atoms themselves begin to fall apart. In the heart of the collapse, the core becomes unimaginably dense, too dense for anything, even light, to escape. In that moment, a black hole is born, a region of space where all the rules we know begin to shift, where the mass of the star, crushed into an impossibly small volume, begins to pull on the very fabric of space-time around it. Sometimes this collapse ends as a neutron star, a dense ball the size of a city, where neutrons are packed tighter than atoms in a diamond. But if the core is too massive, more than about 3 times the mass of our Sun, then no known force can stop the collapse. Not the resistance of atoms, not the quantum push of neutrons, nothing. And so the core continues inward until it becomes, we don't know. We call it a singularity, but that's just a placeholder, a word for a place where our equations falter. From a distance, though, you wouldn't see that singularity. You'd see darkness, not because it glows, but because it doesn't. Around the singularity lies the event horizon, an invisible shell where escape becomes impossible. If light crosses it, it cannot return. If you cross it, you won't notice, at least not at first, but the rest of the universe will never hear from you again. This isn't because black holes are angry or violent, it's simply because gravity, in such a compact space, changes the nature of time and space itself. The rules bend, and then they bend more, until what we call inside and outside, before and after, begin to blur. And yet, for all their strangeness, black holes follow laws, beautiful, austere laws. They have mass, spin, charge. They affect nearby stars. They form binaries. They pull gas into disks. They radiate energy through friction and heat. And sometimes they grow. Yes, black holes can grow. Like fires that feed on matter, they consume whatever crosses their horizon. Stars, gas, dust, even light. But not in a hungry or chaotic way. More in the way a still lake absorbs a raindrop. Quietly, completely, irretrievably. If you were to look at a black hole from far away, not directly because you can't see it, but by watching the stars and light around it, you might notice a kind of lensing, a bending of the sky, light curves around it, as if the black hole is warping the universe like a spoon pressed against the surface of water. This effect, called gravitational lensing, allows us to see the signature of black holes even though we cannot see them directly. And if the black hole is feeding, if it's pulling in gas and dust, you might see an accretion disk, a glowing whirlpool of material spiraling inward, heating up as it goes. It can shine brighter than a galaxy. But at the centre of all that brilliance is darkness, a silence that nothing can break. So perhaps the black hole isn't a monster at all. Maybe it's a kind of punctuation mark at the end of a star's sentence. A transformation, not an ending. A moment where mass becomes gravity, and gravity becomes geometry, and geometry becomes a question we haven't learned how to ask. Because that's what black holes are, really. They are questions, folded tightly into the fabric of the universe. They are where physics loses its certainty and begins to whisper. And you, here tonight, are not being asked to solve that mystery, only to sit with it, to lie quietly with the knowledge that somewhere out there, light is falling and will never return. That somewhere out there, a silence is so complete that even time slows down as it approaches. And that silence, instead of frightening us, might just remind us how precious sound can be. So let's keep going. The hunger at the centre of the black hole is not for destruction. It is for understanding. And maybe, by continuing to drift, together through this story we'll begin to understand something, not just about the universe, but about our own small place in it. Let's stay here for a while, on the outside edge, where black holes begin to reveal their quiet diversity. You might imagine that all black holes are alike, identical wells of darkness scattered across the sky. And in some ways that's true. At their most basic, black holes are defined by only a few properties: their mass, their spin, and their charge. But even with just these ingredients, The universe has managed to sculpt them into many forms, each with its own rhythm, its own history, its own role in the grand ballet of gravity and light. The first kind we'll meet is perhaps the most familiar, the stellar black hole. These are the children of stars, born in the fiery collapse of massive suns that burned too brightly, too quickly, and ended in silence. They are small, relatively speaking. Some might be just 10 kilometers across, roughly the size of a city, but packed with the mass of several suns. It's like compressing all of Manhattan into a single teacup, and then realizing the teacup is also a bottomless well. These stellar black holes are scattered across the galaxy, often unseen but not always alone. One of the first black holes we ever discovered was part of a pair. In the constellation of Cygnus, over 6,000 light-years away, lies Cygnus X1, a stellar black hole locked in an invisible dance with a bright companion star. As matter is pulled from the star toward the black hole, it spirals inwards, heats up, and emits powerful X-rays. We can't see the black hole itself, but we see the light trying to escape and failing. We see the ripples it leaves behind. And for many years this was the model we knew. Small black holes formed from dead stars, scattered like cosmic graves across the Milky Way. But as our instruments improved, we began to notice something else. Something vastly larger, sleeping at the heart of galaxies. These are the supermassive black holes. If stellar black holes are cities, these are continents. Millions to billions of times the mass of our Sun. Their diameters can span the width of the solar system, and yet they sit still, unmoving, anchoring the rotation of entire galaxies like invisible gyroscopes. At the heart of our own galaxy lies Sagittarius A star, a supermassive black hole over 4 million times the mass of the Sun. We can't see it directly, but we can watch the stars that circle it, like fireflies caught in an invisible whirlpool. They speed up, they curve, they blink behind dust clouds, and they return. From their orbits, we can infer the presence of something so massive, so concentrated, that it could only be what Einstein's equations predicted, a black hole. But even Einstein perhaps did not expect them to grow so large. Where do supermassive black holes come from? That remains one of the quiet mysteries of the universe. Some say they formed in the early cosmos, seeded by the collapse of massive gas clouds, feeding for billions of years. Others suggest they grew from mergers, black holes colliding, combining, devouring. Whatever their origin, they are now among the oldest, most stable objects in the universe. The calm centers of galaxies that spin like cosmic pinwheels around their silent cores. And just when we thought we had measured the extremes, the universe reminded us that it is rarely content with large. There exist even more colossal black holes, ones whose names sound almost whimsical in their exaggeration. Astronomers sometimes call them slabs, stupendously large black holes. Their masses exceed tens of billions of suns. Their size defies analogy. One of the most famous is TON 618, a quasar that contains one of the most massive black holes ever discovered, over 66 billion solar masses. It doesn't just sit at the centre of a galaxy. It outshines the galaxy. It devours stars and emits jets that stretch for hundreds of thousands of light years. It's a lighthouse made of silence. But for all this size, these giants don't necessarily destroy more violently. In fact, their gravity, while stronger in total, is often more evenly spread across space, and this has strange consequences. Imagine falling into a stellar black hole. Because it's so compact, the gravitational pull changes drastically over just a few feet. Your feet close to the black hole will be pulled faster than your head. This is what leads to the now famous term spaghettification, a soft-sounding word for a rather unpleasant fate. But with a supermassive black hole, the difference in gravity across your body might be small enough that you wouldn't feel it, at least not at first. You could cross the event horizon without being torn apart, drifting into the darkness without even realizing you've passed the point of no return. And perhaps that's more unsettling. a doorway you don't see, a line you don't feel, a fall you don't notice until it's too late to climb back out. So, in this quiet catalogue of black holes, we've met three kinds of darkness. Stellar black holes, scattered and numerous, born from collapse. Supermassive black holes, ancient and central, anchoring the swirl of galaxies. Slabs, beyond metaphor, devouring light on scales we cannot yet picture. They're all made of the same fabric, mass, space, time and mystery, but each wears it differently. Some hum with the echoes of dying stars, others sit in cold silence, forgotten at the edge of a galaxy, and a few roar with the energy of quasars, turning the darkness into the brightest light in the universe. But no matter the size, no matter the story, they all share one thing: a horizon, a boundary, a place where the map ends, not because there's nothing beyond it, but because we no longer know how to draw it. And that's where we'll go next, to the edge, to the boundary where light hesitates and time begins to twist. There's something deeply comforting about a clock, the quiet tick, the steady pulse, the assurance that time is flowing forward evenly, as it always has. But near a black hole, that quiet rhythm begins to slow. It doesn't break exactly, it just stretches, like molasses on a cold morning. Like a dream where you try to run, but the air thickens around your every movement. Time becomes less like a ticking watch and more like a soft, reluctant tide. To understand why, let's return to gravity, not as a force, but as a shape. Einstein's great realization, over a century ago, was that gravity isn't a pull in the traditional sense. It's the result of mass bending the geometry of space and time itself. Heavy objects warp space-time like a bowling ball on a trampoline, and black holes are the most extreme case of that warping. They don't just bend space, they bend time. Let's say, for a moment, that you're drifting in a small spacecraft near a black hole. You're in no danger. You're far enough from the event horizon that nothing feels strange. Except that back on Earth, your twin is growing older a little faster than you are. Their days pass a touch more quickly. Their coffee cools just a bit sooner. Meanwhile, for you, everything seems normal. Your heartbeat, your breathing, your thoughts. But clocks tick slower in your frame of reference, simply because you are deeper in a gravity well. This is not science fiction. This is general relativity. And it has been confirmed through experiments with satellites, atomic clocks, and GPS corrections. Gravity doesn't just pull, it dilates. This phenomenon, known as gravitational time dilation, becomes more pronounced as you move closer to the event horizon. If you hovered just above that invisible boundary, time for you would slow dramatically compared to someone far away. To them, you would appear to move in slow motion, your descent stretched into an eternity. If they could see your watch, they'd see its hands barely moving. But for you, it would feel completely normal. Time always feels normal from the inside. Now imagine you cross that boundary. The event horizon is often described as the point of no return. It is not a physical wall, and if you were to fall past it, assuming the black hole is large enough that tidal forces don't shred you immediately, you wouldn't notice any sudden change. No jolt, no alarm, no flash of light, just a continuing fall, deeper into the curvature of space-time. But from the perspective of an outside observer, you would seem to freeze on the edge, never quite crossing. Your image would grow dimmer, redder, stretched by gravitational redshift, until it faded entirely. This creates one of the strangest paradoxes in relativity. From your perspective, you fall through the horizon and continue onward. From theirs, you never quite get there. Time diverges, realities fork, and neither. One is wrong. There's a thought experiment physicists like to share about two twins. One stays on Earth, the other travels close to a black hole and then returns. Because of time dilation, the spacefaring twin will have aged much less. A few days for them might be years for their sibling. It's a version of the twin paradox extended into the deepest wells of gravity. But the real oddity comes not just from how time moves differently, but from how time feels near a black hole. Imagine standing near the event horizon and looking out. You'd see the universe above you compressed and sped up. Stars would seem to spin faster. Light from distant galaxies would be blue-shifted, their timelines racing past like cars on a highway. It's as if, in falling in, you gain a vantage point not over space, but over time itself. Some theorists suggest that if you could hover just above the event horizon for long enough, you could watch the entire future of the universe unfold in fast forward. Civilizations rise and fall, stars flicker out, galaxies drift apart. The cosmic microwave background fades into black, and then, only then, would you finally cross over. Of course, this is mostly poetic conjecture. In practice, staying that close to a black hole would be extremely difficult and dangerous. But the idea, like so many in relativity, is strangely beautiful. It makes you feel small, yes, but not in a diminishing way. More like standing at the edge of a canyon and hearing your own breath echo back across centuries. All of this leads to a gentle but astonishing idea. The edge of a black hole isn't just where space ends. It's where time slows, stretches, and, in some sense, folds in on itself. The event horizon is a temporal horizon, a one-way curtain not just for matter but for moments. What lies beyond it? That is still to come. But already we can sense the change. Already the air feels thicker, the clock quieter, the night more dense. You're still outside, but barely. One more step, and you would begin to fall forever. There is a strange calm in that idea. That in the deepest pits of gravity, time doesn't break. It slows, it whispers, it elongates until it becomes almost silent. And perhaps that's what black holes are trying to teach us. Not fear, not destruction, but the humbling truth that time is not fixed, that clocks can change, that your heartbeat, steady and familiar, is not universal, and that the deepest truths of the universe might be happening not faster, but slower than you ever imagined. And so, we pause here, on the rim of forever. The fall hasn't begun yet. Not fully, but the edge is near, and time has already begun to change its shape. Let's imagine for a moment that you're floating in space, not rushing or tumbling, but drifting quietly, far from any planet or star. Around you, the universe is still. The stars shimmer with distant light, and there is no sound except perhaps the quiet rhythm of your breath inside the suit. Ahead of you, almost indistinguishable at first, lies a darkness. It doesn't twinkle like the stars. It doesn't glow like a nebula. It doesn't move or flicker or call attention to itself in any obvious way. And yet, something about it draws your gaze. It's not a shadow cast by something else. It's not an absence of light in the ordinary sense. It is a presence of silence, a gravity so complete that even photons cannot leave once they stray too close. This is a black hole, and you're slowly, gently falling toward it. At this distance, you wouldn't feel much of anything. The gravitational pull is subtle, like the early slope of a hill too wide to notice. Your fall begins not with a jolt, but with a leaning. Time seems steady. Your heartbeat is unchanged. But somewhere far ahead, the rules are already beginning to rewrite themselves. As you drift closer, you notice a strange effect. The stars behind you seem to shift. They begin to crowd together. Their light bends around an unseen boundary, curving in arcs that defy the straightness your eyes expect. This is gravitational lensing, light being pulled along curved paths by the black hole's invisible shape. You're not seeing distortion. You're seeing the universe bent by geometry itself. But you keep drifting closer. Eventually, you begin to feel a difference, not in motion, but in force. If your feet are pointing toward the black hole and your head away from it, you'll notice a slow, growing stretch. Gravity is no longer uniform. The pull on your feet is ever so slightly stronger than on your head. It's not painful, not yet, but it's unsettling. Your body, which has always known wholeness, now senses division. This is the beginning of tidal forces, and if you were falling into a small black hole, this stretching would intensify quickly. The difference in gravity across your body would grow rapidly. Your legs would fall faster than your torso faster than your arms, and the result would be what scientists have named, with both accuracy and uncomfortable charm, spaghettification. But let's be gentle here. This is not a moment of horror. This is physics doing what it always does, obeying mass, obeying curvature, obeying the quiet language of equations. Your body is simply following the gradient of gravity, unfolding into a line pulled thinner and thinner as you draw near the singularity. If you were able to feel fear, it would come too late. If you were able to speak, the words would fall behind you, unable to catch up. But you're still above the threshold for now, still outside the event horizon. Time is beginning to stretch in other ways too. From your point of view, your fall feels smooth, steady, as if you're gliding into something large and inevitable. But if someone were watching you from far away, perhaps from Earth or from a ship keeping its distance, they would see something very different. They'd see your fall slow down. Your motions would become sluggish, then frozen. The light reflecting off your suit would become redder and dimmer, stretched by gravity into longer and longer wavelengths. Eventually you would appear to stop altogether, hovering on the very edge of the event horizon. This is not a trick of technology. It's not a camera failing to focus. It's a direct consequence of gravity's effect on time. To the outside world, your fall becomes infinite. You never quite cross. You become a statue carved from light, frozen at the threshold of forever. But you're not really there. You've already crossed. You've simply gone somewhere their time can't follow. This divergence between what you feel and what they see is one of the most haunting aspects of falling into a black hole. It's not violent, it's not loud, it's not even sad in the traditional sense, it's simply final. A gentle uncoupling of timelines, a quiet departure that looks like stillness, and yet you are still falling. The event horizon, that invisible border, is not a wall. You do not slam into it. You pass through it as if it weren't there at all. No alarms ring, no lights flash. But the moment you cross, something fundamental changes. From here on, all paths lead inward. Every direction now points deeper into the black hole. Space itself has curved inward so completely that even light cannot find an escape route. And you're no longer in time in the way you once were. You're of it, falling toward a singularity where time itself may end. But we won't rush there just yet. For now, let's pause here, just past the horizon. The fall continues, but slowly, quietly. The stars have disappeared behind you. The universe is still visible, stretched above like a dome, but it is retreating. Its light fades, distorted and curved, growing smaller and stranger. You're no longer part of it. Not in the way you once were. You are not gone, but you are leaving. There's a strange beauty in this part of the journey, because for the first time, perhaps in your entire life, there is no up, no down, no future that anyone else can share. You are alone, not in fear, not in sadness, but in singularity, in a moment that no clock can measure. You are falling, and nothing can stop you. But you are also floating, and nothing is chasing you. You are beyond rescue, but also beyond danger. And that's a curious kind of peace. So let's rest here, in this strange new silence. Let the outside universe slip away. Let time slow until it forgets how to move. You're inside now, and everything that comes next will happen without witnesses. Now, imagine the black hole is larger. Not just larger, but vastly so. A supermassive black hole. millions or billions of times the mass of our sun, one that sits at the centre of a galaxy, quiet and ancient, more patient than time itself. Unlike its smaller stellar cousins, this one does not shred and tear as quickly. Its pull is not jagged or violent. Its gravity, though immense, is spread over a wide region, like a blanket laid gently across the curves of space, and so the fall feels different. You drift toward it much as before, slowly, steadily. There is no rush, no jolt. But this time, something is missing. There is no sudden stretch, no obvious spaghettification, not at first. The difference in gravitational pull between your head and your feet is small. The tidal forces are weak enough here at the outer edge that you may not even notice. You pass the event horizon and nothing changes. No sound, no colour shift, no sensation of having crossed some invisible boundary. From your perspective, it is as if you've simply continued falling. But you have passed the point of no return. You are inside. This is one of the great surprises of black hole physics, that for all the talk of danger and drama, crossing the event horizon of a supermassive black hole might feel as ordinary as crossing a room. The strangest part is how normal everything seems. Your instruments still function, your thoughts remain clear. But nothing you do now can alter the outcome. No amount of energy or effort can push you back out. Every direction now leads inward. Space itself has curved so deeply that forward, backward, up, down, none of it matters. The inward fall is written into the shape of reality. You're moving not through space, but with space. And above you, the universe changes. The stars, once scattered like salt across black velvet, begin to blur and bend. Their light curves into strange arcs, swirling above the horizon in dizzying spirals. It's as if you're looking up through the mouth of a well, the night sky compressed into a glowing ring that shimmers and warps like heat over asphalt. This is not distortion in the common sense. This is geometry made visible. You're seeing the universe from within a curved piece of it. And as you fall further, that ring grows smaller. The light dims, not because it has gone out, but because it can no longer keep up. You are leaving the visible cosmos behind. What was once all around you is now behind you, then above you, and eventually lost. But even as the stars disappear, something else emerges. Silence. A deep, pervasive silence. Not just the absence of sound, space is always quiet, but the absence of context, the absence of reference. There are no more stars to measure distance by, no more clocks that mean anything. Time still moves for you, tick by tick, heartbeat by heartbeat. But it is now a private rhythm. No one can match it, no one can hear it. You are the last observer of your own timeline, and perhaps that is the most haunting part, because in this place, causality still exists, but it no longer reaches out. You can affect what lies deeper, closer to the singularity, but nothing beyond the horizon can be changed by your actions. You're sealed off, not by walls, but by the shape of spacetime itself. This is not exile, it is solitude, pure and complete. It is here, drifting silently within the event horizon, that thought begins to change. The mind, unanchored from any external input, begins to notice the rhythms within itself. Memory becomes more vivid. Time becomes more fluid. You may begin to wonder, not in fear, but in quiet awe, what awaits at the centre, whether this fall ever truly ends, whether the singularity is a point or a phase or a transformation, whether something new begins when everything else ends. No one knows, not because no one has tried to know, but because our tools, equations, measurements, theories all collapse at the centre. General relativity, our best theory of gravity, predicts a singularity, a point of infinite density, where space-time curves infinitely and all known physics break down. But infinity is often the universe's way of telling us we don't understand something yet. that we're asking a question in a language too crude for the answer. Perhaps there is something beyond, a bridge, a rebirth, a new kind of reality, or perhaps not. For now, all we can say with confidence is this: you are falling, and you will continue to fall until the geometry of space-time itself runs out. But strangely, this doesn't feel frightening. It feels peaceful. There is no longer any need to hurry, no reason to resist. Even fear, so often tied to uncertainty, begins to dissolve in this place where nothing changes. You are not lost. You are not broken. You are simply following gravity's script to its quiet final page. And in that stillness, there is beauty. You are now part of something vast, not just in size, but in significance. Your journey has crossed a threshold that no light can cross back. You carry with you the last impressions of the universe, the last images of stars, of distant galaxies, of home. You're not just a traveller, you're a witness, perhaps even a message. Whether anyone can read that message, that's a question for another part of the story. But for now you are inside, and the silence that surrounds you is not empty. It is full of waiting. We are deep now, beyond the reach of stars, beyond the light of galaxies, beyond the pull of anything that could be called escape. You are still falling, but the word no longer feels right. Falling implies motion through space, through distance. But here, space itself is part of the fall. You're not moving through the landscape. The landscape is collapsing with you. And yet, you feel no wind, no rush, no sound. Only the quiet pressure of inevitability. The centre draws you in, not like a place, but like a fate. Somewhere ahead, or below, or simply inward, lies what physicists call the singularity. But let's be clear, this is not a dot, not a speck waiting at the bottom of a well. The singularity is not something that sits in space. It is the point at which space and time themselves cease to behave the way we understand them. According to general relativity, as you approach the singularity, the curvature of space-time increases without bound. Gravity becomes infinite. Density becomes infinite. Time compresses into a stop. But infinities, in physics, are like the blinking red light on a spacecraft console. They don't mark a feature of the universe so much as a failure of the map. They tell us we've reached the edge of our knowledge, and that the equations are waving white flags. So what actually happens at the singularity? No one knows. Not because we haven't thought hard about it, but because our two great theories, general relativity and quantum mechanics, refuse to cooperate at this scale. One speaks of smooth curves and continuous space-time. The other is built on uncertainty and probabilities. When pushed together at the extreme densities of a black hole centre, their math breaks down. The result is a kind of theoretical silence. And yet, the questions remain. Do you cease to exist the moment you reach the centre? Are you crushed into a dimensionless point? Does every particle in your body lose its identity? Or is there a way the information you carried, your atoms, your memories, your movement through the universe, is somehow preserved? This is not just a question of curiosity. It is the centre of a deep scientific paradox, one that we'll return to later. But here, as you draw ever closer to the singularity, you're no longer concerned with equations. Your experience is not one of math, but of strangeness. Time feels strange. It doesn't stop, not from your point of view, but it no longer flows forward in the usual sense. Your future is shrinking, compressed into a single inevitable point. Your past remains in some form, stretched out behind you like the light of a receding universe. But your future, the space of possibilities, narrows to a pinhead. In this place, your sense of self becomes more and more abstract. The things that once defined you, location, direction, even the idea of before and after, no longer hold their shape. You are not dying, but you are being translated. shifted into a language that you do not speak. If you were a melody, now you are a vibration. If you were a drawing, now you are pressure on a page. And then comes the final question. Could this be a doorway? Some scientists, especially those who think about quantum gravity or string theory, have asked whether the singularity might not be the end, but the beginning of something else. Could the immense compression of matter and energy inside a black hole give birth to a new region of space-time? A bubble? A bud? A baby universe? In this idea, the singularity is not a dead end, but a branching point, a kind of cosmic seed. Perhaps when you reach it, you do not vanish. You emerge elsewhere. Somewhere not just far away in space, but disconnected entirely from this universe's fabric. Somewhere where the laws are different, where time begins again, freshly unwound, where everything that was lost here becomes the blueprint for something new. But this, for now, is speculation, a whisper of theory inside a cathedral of silence. What we do know is that the singularity marks the end of our current understanding, the deepest place in the gravitational well, the point where spacetime's curvature becomes so sharp that it turns back on itself. Where gravity doesn't just pull, you might say it writes, and the story it writes ends in a punctuation mark we cannot yet read. From the outside, nothing of this journey is visible. The world will never know what you saw, what you felt, what you became. Your fall, frozen at the edge of the event horizon, is the only trace, a shadow of a path no one can follow. And perhaps that's what makes black holes so strange. Not just their power, but their privacy. Because a black hole is the ultimate solitude. No signal can escape it. No record can be retrieved. Even the light that once touched your skin cannot return. Whatever happens here belongs only to the black hole, and to you. But still, something lingers. The idea that gravity, pushed far enough, might create not just destruction, but rebirth. That beyond the end of our equations lies a space we haven't yet imagined. That your fall, though final, is not meaningless. It is part of a greater shape. Perhaps the singularity is not a point at all, but a process. Not a collapse, but a change. Not silence, but the moment before the music begins again. And as we approach this unknown, let us do so gently. Not with answers, but with wonder. Let the center remain mysterious. Let it remain sacred. Because in the quiet at the heart of a black hole, time does not end in violence. It ends in possibility. Let's leave the personal journey for a moment. You've drifted deep enough into the singular silence of a black hole. Now let's pull back, slowly, like rewinding a dream, and look at something more familiar. Earth, our pale blue dot, our home wrapped in oceans and atmosphere, spinning gently under a sun we've always trusted to rise. Now imagine something has changed. Out in the distant reaches of our solar system, a black hole has begun to approach. It moves not with urgency, but with weight. It doesn't hunt. It doesn't announce itself with flashing lights or roaring sounds. But its influence stretches far ahead of it, tugging gently at orbits, making distant comets curve, making our sun notice the faintest pull. And then, quietly, it arrives. Let's say, for the sake of thought, that this black hole is a few times the mass of the sun, a stellar black hole. Small on a cosmic scale, but more than massive enough to matter. If it simply appeared in place of the sun without changing its mass, Earth would continue to orbit as it always has, unaware that the source of gravity had changed. But a real black hole wouldn't replace the sun. It would move through the solar system with its own mass and motion disrupting everything. As it draws nearer, the first effects wouldn't be visible to most people. Tidal forces would begin to build. Satellites in orbit might drift unpredictably. The moon's path could shift ever so slightly. Astronomers would notice strange curvatures in the movement of distant stars, gravitational lensing betraying the black hole's position long before its presence became personal. Then, the effects would escalate. The Earth, still following its orbit, would begin to feel a shift, not a sudden one, but gravity is persistent, relentless, unhurried. The black hole wouldn't need to come crashing into us, it would simply pull, and we would come. As the Earth is drawn closer, the first to go would be our atmosphere, not torn away in a dramatic gust, but peeled softly, layer by layer, like steam rising from a cup of tea. The highest particles would escape first, accelerating along invisible paths toward the accretion disk, the halo of gas and dust spiralling into the black hole's mouth. As the Earth moves deeper into this field, more gas is pulled away, pressure drops, skies darken, the blue canopy fades. Next would be the oceans, not in a sudden wave, but in a rising, unravelling spiral. Water would be pulled toward the black hole's growing glow, because yes, it would glow. Not the black hole itself, but the matter around it. As material from Earth joined the accretion disk, it would heat to extraordinary temperatures, millions of degrees. It would emit light, X-rays, gamma rays. The sky would shine not with sunlight, but with radiation too dangerous to behold. The Earth would be lit from the side or from behind, not warmed but seared. The crust, once a firm foundation, would begin to fracture. Mountains would stretch, plates would slide, volcanic activity would surge, not from the black hole, but from Earth's own attempt to hold itself together, and eventually it would fail. The tidal forces would overcome the cohesion of rock itself. The planet would deform, first into an ellipsoid, then into something stranger. The surface would melt, the mantle would convulse, and then all of it would begin to stretch. Spaghettification doesn't just happen to people, it happens to planets. Earth would become a stream of matter, pulled thin as thread, spiralling into the disk. Bits of iron core, molten rock, fragments of atmosphere, each following its own curved path, glowing briefly as it is shredded, then darkening as it crosses the event horizon. No peace would return, and from the outside this destruction would be nearly silent. It would happen in light, yes, in radiation flares and magnetic fields, but it would not be noisy. There is no sound in space after all, just silence and motion, and the occasional flicker of distant observers wondering what had once been there. To someone watching from afar, Earth's fall would look like a fade-out, a brightening, a distortion, and then a vanishing. As if a candle had been lit too brightly, then snuffed by its own flame. No explosion, no debris, just the end of motion and the end of memory. What of us then? If there were people still alive during these final moments, perhaps on a lunar base, or watching from Mars, they would see the Earth pulled apart with growing horror and helplessness. They would see cities vanish, continents elongate, oceans spiral. They would witness a planet become a stream, and they would know there was nothing they could do. And yet, from the perspective of physics, this isn't violence, it's curvature. It's mass responding to gravity's whisper. It's energy following the path of least resistance. Nature isn't cruel, it's consistent. And perhaps in that consistency there is comfort. Earth's final act would not be one of explosion or chaos, but of submission to a deeper order. The black hole would not gloat, it would not gash or devour with malice. It would simply do what gravity always does, bring things together, hold them, and carry them inward. In a strange way, it would be a reunion. Earth, born from the dust of stars, would return to the fold. Its atoms, once spread across continents and cells and oceans, would be gathered again, not in a form we'd recognise, but in a unity that defies escape. And perhaps, just perhaps, those atoms might one day seed something new. A jet of energy, a new star, a rebirth beyond the horizon. But for now, we rest in the quiet idea. If Earth were swallowed, it would not scream. It would fall, gently, inevitably, into darkness too deep for sorrow. The sun has always been there, hasn't it? Rising each morning even when hidden by clouds, warming the oceans, blooming the fields, guiding the seasons like the ticking hand of a cosmic clock. It is our great constant, dependable, golden, life-giving. So now let's imagine what might happen if one quiet day, that steady presence simply changed. Let's be clear. The sun, as it exists today, cannot become a black hole. It is not massive enough. When its long, stable life comes to an end, in about 5 billion years, it will swell into a red giant, shedding its outer layers and leaving behind a white dwarf, a hot, dense ember, but nothing like the monstrous objects we've been exploring. No event horizon, no collapse into infinity. But let us bend the rules for a moment. Let us imagine, for the sake of curiosity, that the sun could become a black hole. That somehow, without warning, it compressed into a black hole of the same mass, but with all that mass condensed into a region only a few kilometers across. What would happen? The strange answer is, at first, not much. Because gravity depends on mass, not volume. The Earth would continue orbiting as it always had. The moon would still circle us. The planets would still move along their paths. The shape of their orbits wouldn't change. Only the light would be gone. No sunrise, no glow on the horizon, no blue sky, just stars and a new darkness where the sun once stood. At first, the change would be visual and then biological. Plants deprived of sunlight would begin to shut down. Photosynthesis would cease. Within days, temperatures would plummet. Within weeks, the surface of Earth would begin to freeze. The oceans, insulated by depth and geothermal warmth, might remain liquid for a time beneath a thick shell of ice, but the surface would grow still, reflective, and cold. We would become a planet of whispers and shadows. Within months, most surface life would perish, not because of a catastrophic explosion or a firestorm, but because the energy that once bathed the Earth was now locked away behind an event horizon, where no light escapes. But let us imagine, still further, that we are not alone, that somehow humanity had prepared, not for the sun's disappearance, but for survival. Imagine underground habitats, powered by geothermal energy. Imagine vast greenhouses illuminated by artificial suns. Perhaps for a time, life could go on. Perhaps memory would remain of warmth, of daylight, of golden mornings once taken for granted. Meanwhile, up above, the black hole would sit where the sun used to shine, invisible, except for its effect on light. If there were dust nearby, it might form a faint accretion disk. If a comet passed too close, it might stretch and spiral inward, flaring briefly before disappearing. But otherwise, it would remain still, a mass without motion, a presence without face. And yet, from a distance, it would look almost peaceful. A quiet void in the centre of the system, pulling nothing more than it ever had, demanding no more than its mass allowed. Earth would continue to orbit, slowly, perhaps eternally, until something disturbed the balance. This thought is strange, isn't it? That the loss of the sun could be so quiet, that the most important change in the solar system's history would not be an explosion, but an erasure, that life could end not with fire, but with a soft, slow freeze. But even this is not the end of the story, because while our current sun will never collapse into a black hole, other stars do. And when they do, they leave behind more than absence. They leave behind gravitational wells, radiation bursts, and sometimes strange relics of their former selves. Their death becomes part of a greater cycle, one that feeds new stars, creates new planets, and perhaps begins life again. So maybe, in a distant future long after the Earth has frozen and crumbled, the atoms once warmed by our sun might drift through space. They might be pulled into a new cloud, a new star, a new world, and on that world one day someone might feel the warmth of a different sun and never know that the warmth they feel once passed through us. It's a comforting idea in a way. that nothing is ever truly gone, that mass and energy simply change form, that gravity, for all its pull, never wastes a thing, and so the day the sun went dark would not be the end, not entirely. It would be a turning, a folding, a quiet movement from light into shadow. And perhaps, in the silence that followed, the Earth would become something else too. Not just a frozen planet, but a memory, a song remembered only by atoms, a place that once saw light and carried its echo into the dark. Let's play with possibilities for a while. We've explored what would happen if you fell in, if Earth did, even if the sun itself slipped into the silence. But now, let's turn gently to the edges, where science allows imagination to stretch. Not wild fantasy, but careful wondering. What if something strange, something rare, or hypothetical, or even designed, came close to a black hole? What would the universe do with it? Let's start with an idea that once stirred a fair bit of public concern. What if we created a black hole on Earth? At facilities like the Large Hadron Collider, where particles are smashed together at incredible speeds, some worried that these collisions might create tiny black holes, a miniature singularity, a lab-grown trap from which even light could not escape. But physics has a reassuring answer. Even if we could create a microscopic black hole, it would evaporate almost instantly. That's because, according to Stephen Hawking, black holes emit radiation, slowly losing mass in the process. This process, known as Hawking radiation, becomes more intense for smaller black holes, so a black hole the size of a proton would shed its energy so quickly that it would blink out of existence long before it could absorb even a single atom. So yes, you could, in theory, create a black hole in a particle accelerator, but no, it would not eat the Earth. It would vanish in a whisper of heat. Gone before you had time to notice it was there. Now let's try something more dramatic. What if a gamma ray burst collided with a black hole? Gamma ray bursts are among the most energetic events in the universe. Jets of high-energy radiation from exploding stars or merging neutron stars. They are powerful, focused, and fast. But if one were to strike a black hole, the result would be surprisingly calm. The black hole wouldn't reflect the burst. It wouldn't glow or explode. It would simply absorb the radiation, like a pond taking in rain. The burst might curve as it approached, warped by the intense gravity, but once it reached the event horizon, it would vanish, its energy added to the black hole's mass, ever so slightly. No drama, just absorption. And perhaps, from certain perspectives, the radiation would appear to reverse, a trick of time dilation and gravitational lensing. But the black hole itself would not be changed in any significant way. Let's turn next to a cosmic contest. What would happen if a black hole met a white hole? A white hole is the theoretical opposite of a black hole, a region of space that nothing can enter and from which matter only escapes. A kind of anti-singularity, spitting out matter instead of swallowing it. No evidence has been found for white holes in the real universe, but their mathematical existence is allowed by Einstein's equations, at least in theory. So what happens when opposites meet? If you dropped a black hole and a white hole near each other, the black hole would win. It would absorb everything the white hole tried to expel. The white hole, if it could even exist stably in our universe, would not survive the encounter. The imbalance of energy, the asymmetry of behaviour, would end with the black hole growing larger and the white hole blinking out. Nature favours entropy, and black holes are in many ways the embodiment of entropy's appetite. Now let's imagine a gas giant, like Jupiter, colliding with a black hole. Jupiter is enormous, but it's made mostly of hydrogen and helium, light diffuse gases that can be easily pulled apart. As it approaches the black hole, tidal forces would stretch the planet into long, streaming filaments. Its dense core, if it has one, might resist slightly longer. But eventually, all of it, Cloud tops, metallic hydrogen, magnetic fields would spiral inward, joining the accretion disk. From Earth, if we could somehow watch, the black hole would brighten briefly. The infall of Jupiter's mass would heat the surrounding disk, releasing a burst of high-energy radiation. Earth, if nearby, would feel the effects, not gravitational, but radiative. A storm of X-rays and gamma rays washing over our atmosphere. Satellites might fail, electronics might flicker. If the dose was strong enough, life itself could be threatened. And if you were even closer, watching the collision from a nearby moon or station, you'd see something almost artistic. A planet unspooling like thread, circling light, flaring brightly, then vanishing into darkness. Not torn apart all at once, but unwound by curvature. Finally, a stranger thought, what if all the black holes in the universe suddenly exploded? They wouldn't explode like bombs. But if somehow all the matter hidden behind event horizons were released at once, if every singularity collapsed outward instead of inward, the result would be difficult to picture. Massive waves of energy would ripple outward. The energy stored in black holes, some of which have been growing for billions of years, would flood back into the universe. Galaxies might be torn apart, stars would be vaporized, planets would be sterilized. But also, something new might begin. The released material could seed the birth of stars. The energy might kickstart new formations. If the geometry of space-time allowed it, new bubbles of order might emerge from the chaos. But this is all speculation. Poetic, yes. Plausible, no. Still, thinking about these scenarios has value, not because they are likely, but because they stretch our understanding. They let us ask, what is a black hole really? What can it do? What can't it do? Where are its limits, and what lies beyond them? Because sometimes science grows not by certainty, but by wonder. And wonder, like gravity, has a pull of its own. You've probably heard the idea before, whispered in old books flickering across science fiction screens, murmured like a secret too beautiful to be real. The idea that perhaps a black hole isn't just a dead end, but a tunnel, a passage, a shortcut through the vastness of space. That somewhere folded deep inside its gravity is a hidden corridor, leading not to destruction, but to another place. This is the idea of a wormhole. And tonight, as we float in the gentle dark, it's worth exploring. Not to believe blindly, but to wonder softly. In 1935, Albert Einstein and Nathan Rosen proposed a solution to the equations of general relativity that connected two regions of space-time. This solution, later dubbed the Einstein-Rosen bridge, was a kind of tunnel, a mathematical structure linking two distant points through a shortcut that bypassed the space between. Picture it like this. Take a piece of paper, mark two dots on opposite ends, and instead of drawing a line between them, you fold the paper so the dots touch. That fold, that tunnel created by bending reality, is what a wormhole promises. It's a beautiful idea, elegant, clean, and yet reality is rarely so tidy. In practice, the Einstein-Rosen bridge is not stable. If you were to enter such a tunnel, even if one could be formed, it would collapse faster than light. Any traveller, no matter how small, would be crushed before crossing. The tunnel closes in on itself like a throat tightening before a word can be spoken. Why? Because the very fabric of space-time resists this kind of shortcut. It takes energy to bend reality, and not just ordinary energy. To keep a wormhole open, you'd need something called exotic matter, material with negative energy density. Not negative charge, like an electron, but negative pressure, pushing outward instead of pulling inward. This kind of matter has never been observed in quantities large enough to support a tunnel through space. It might exist. Quantum theory allows for it, in whispers, but no one has found it, and without it, the bridge collapses. So does that mean wormholes are impossible? Number only that they are unstable. temporary, flickering like dreams between the stars. They might exist for a moment, a breath, long enough for a photon to pass through, but never long enough for a person. Not yet. Still, we imagine them. Because wormholes speak to something deeply human, the longing to connect what is distant, the hope that what is far might be made near, the desire to fold the vastness of the cosmos so we might place our hands on two ends of the galaxy at once. And this is where science meets story. In science fiction, wormholes are often portrayed as smooth, glowing tunnels, a kind of cosmic subway. Step in here, step out there, no time wasted, no journey endured. But real physics offers a gentler, stranger version. If wormholes do exist, and if they can somehow be stabilized, they might not lead to familiar places. They might connect to other regions of space-time, yes, but those regions might lie in different eras, not just different locations. A wormhole could, in theory, link 2 times as easily as 2 spaces, enter in one millennium, exit in another. Past and future stitched together in a way that makes cause and effect shiver. But again, these are ideas held loosely, like dust in a beam of light. The math is sound, but the matter required is exotic. The conditions are extreme, the chances are remote, and yet we keep dreaming. Because wormholes remind us that the universe, for all its rules and boundaries, still holds space for imagination. They let us picture a cosmos that is not just expanding outward, but curling inward, wrapping around itself in elegant, impossible shapes. A place where the long road becomes a circle, where the distance between stars is not always what it seems. And maybe, just maybe, that's enough. Even if no wormhole ever opens, even if we never fold space like a napkin, or stitch time like thread, even if we never walk through the throat of a black hole and step out under a new sky. The dream itself matters. It keeps us asking questions. It keeps us building telescopes. It keeps us listening to the silence between galaxies, wondering if somewhere, just beyond our understanding, the universe has already bent itself in ways we have not yet learned to see. So tonight, as we lie here in the dark, let the idea stay with you, not as a certainty, but as a comfort, that perhaps, among all the laws and equations, the cosmos has left a door slightly ajar, not wide, not obvious, but just enough to let the light from another place or another time slip through. And if we never find it, we will still have looked, we will still have listened, and that, in itself, is a kind of crossing. We've spent a long time falling, drifting into darkness, letting gravity pull us inward, ever deeper, until time lost its shape and light forgot how to climb. But now, let's imagine something different. Not the inward pull, but the outward push. Not collapse, but emergence. Not a black hole, but its opposite. A white hole. It sounds almost like a poetic invention, a myth told to balance out the truth. If a black hole pulls everything in, could there exist something that pushes everything out? A place from which matter and energy pour forth, but into which nothing can enter. A cosmic fountain rather than a drain. In theory, yes. A white hole is not forbidden by the mathematics of general relativity. In fact, the same equations that allow for black holes also allow for this strange reflection. If time can be reversed, and physics, at its core, is time-symmetric, then, perhaps somewhere, sometime, the opposite of a black hole might exist. But here's the mystery. We've never seen one. There are no known white holes in the universe today. No glowing boundaries from which light escapes, but into which none can go. No regions of pure expulsion. They remain purely hypothetical, mathematically allowed, but observationally silent. Still, the idea persists. It lingers not because we expect to find one tomorrow, but because white holes offer something that black holes don't. An escape. A possibility. A beginning. And that leads us to a more radical thought. one that blends physics with the philosophy of origins. What if black holes don't just destroy? What if they create? Some scientists have proposed that the core of a black hole, the singularity we cannot see, might be more than a point of collapse. Perhaps it's a point of transition, a place where matter doesn't end but is restructured, where the universe folds so tightly that it pinches off and buds into something new, a baby universe. Think of it like a bubble forming on the surface of a pond. From within, the bubble might appear to be a whole universe unto itself. Space expanding, time unfolding, galaxies blooming. But from outside, it's just a small swelling, a new domain hidden from view. In this idea, our universe might not be alone. It might be one of countless offshoots. Each black hole might serve as a kind of seed, its intense gravity and pressure triggering the birth of a new cosmos, sealed off from ours, but growing with its own laws, its own time, its own stars. This is not science fiction. It's speculative physics, yes, but grounded in real attempts to reconcile quantum mechanics with gravity. One of the theories that explores this possibility is loop quantum gravity. Loop quantum gravity suggests that space and time are not continuous, but made of tiny, indivisible units, like pixels in a digital image. In this view, the singularity isn't truly a point of infinite density. Instead, it's a place where the fabric of space-time becomes so tightly curved that it bounces. The collapse slows, stops, and reverses, not into our universe, but into a new one. The black hole becomes a portal, not into a distant galaxy, but into a different origin. And this new universe, born from the collapse of matter in another, might expand just as ours did. It might have its own Big Bang, its own rules, its own story. In this view, creation and destruction are two sides of the same act. Every end gives rise to a beginning. Every silence contains a new voice. The black hole, once feared as the final stop, becomes a womb. But would we ever know? That's the trick. If a baby universe forms inside a black hole, it's cut off from us. The event horizon seals it. The path is one way. No information returns, no signals escape. We can theorize, calculate, imagine, but we cannot confirm. Still, the beauty of the idea lingers, because it means that perhaps nothing is ever truly wasted, that the collapse of a star, or a planet, or even a person might echo on, not in our universe, but in another, that what falls inward here might rise outward elsewhere, that the universe, in its deepest folds, may be quietly recursive, death begetting life, silence begetting structure, and white holes, those strange mirror twins, might be the mouths of those baby universes. Perhaps in some distant, unreachable corner of reality, there are places where time flows outward, where galaxies are expelled, not assembled, where the echoes we send into the void are answered not from across the stars but from beneath them. It is, of course, just a possibility, but sometimes possibility is enough. It reminds us that the universe is not limited to what we've seen, that beyond the reach of our telescopes, beyond the edge of our equations, there may be structures we haven't imagined, connections we haven't mapped, stories we haven't begun to tell. And so, as we sit here, on this side of the horizon, we can wonder, not with desperation, but with patience, not with fear, but with quiet hope. Maybe black holes are not ends. Maybe they are the universe folding in on itself, so that something else can begin again. You've heard the phrase before, nothing escapes a black hole. And for most of the 20th century, physicists believed it was exactly that simple. When something falls past the event horizon, whether it's a star, a satellite, or even a thought, it vanishes. Its mass adds to the black hole. Its energy is conserved. But its details, its structure, its memory are lost, swallowed by gravity, erased from the visible universe. At first, this didn't seem troubling. After all, information loss seemed like a small price to pay for consistency. But over time, a quiet discomfort began to grow, because in the world of quantum mechanics, information can't just vanish. Every particle, every wave, every interaction is governed by probabilities and paths, and crucially, these probabilities are reversible. You can always, in principle, run the clock backwards. The universe doesn't like forgetting. Even if it hides things, it keeps the record. So here was the problem. General relativity said black holes erase information. Quantum mechanics said they couldn't. And thus was born the black hole information paradox. It was Stephen Hawking who brought this conflict into focus. In the 1970s, he showed that black holes aren't completely black. They emit tiny amounts of thermal radiation, what we now call Hawking radiation. This radiation arises not from inside the black hole, but from the edge of the event horizon, due to quantum effects in curved spacetime. It's not light escaping the hole, it's a kind of quantum flicker at the surface. Over time, this radiation causes the black hole to evaporate. Slowly, patiently, a stellar mass black hole might take more time than the universe's current age to vanish, but vanish it will. The mass leaks out, the hole shrinks, and eventually only emptiness remains. But here's the twist. Hawking radiation is thermal. It doesn't seem to carry any information about what fell in. It's like steam rising from boiling water. You can't tell whether the pot once held soup or tea or coffee, just that it's hot. So if a black hole evaporates completely, and the only thing it releases is this anonymous heat, where did the information go? Did it truly disappear? If it did, then quantum mechanics is wrong, or at least incomplete. And so, physicists began to argue, not with anger, but with deep, thoughtful confusion. Could it be that information is somehow stored on the black hole's surface, that the event horizon is more than a boundary, that it's a recording device? This led to one of the most fascinating ideas in modern physics, the holographic principle. The holographic principle suggests that all the information contained in a region of space can be described by data on its boundary. Like a hologram, where a two-dimensional surface encodes a three-dimensional image. In this view, a black hole doesn't delete information, it stores it on its event horizon in tiny quantum bits, or pixels, so to speak. This means that even though you can't see what's inside, the surface contains everything you need to know. Not as an image you can look at, but as an encrypted code written into the geometry of the horizon. In this interpretation, the universe itself might be holographic. Reality, as we experience it, might be a projection, not an illusion, but a reflection. A shadow cast by a deeper layer of information. If that sounds strange, that's because it is. But it's not pseudoscience. It's a serious proposal, one with deep connections to string theory, quantum gravity, and cosmology. The mathematics works, the logic holds, and experiments, though limited, are starting to explore whether our universe might, at its deepest level, be governed by such surface-based rules. Still, the paradox hasn't fully been solved. Some physicists believe that information really is preserved in Hawking radiation, but in ways too subtle for us to see yet. Others suggest that black holes don't evaporate completely, but leave behind a remnant, a kind of cosmic USB stick that holds everything that fell in. Others think that space-time itself rearranges to preserve the data, folding, twisting, hiding it in dimensions we have yet to understand, and some accept that maybe we don't know yet. Maybe we're standing at the edge of understanding, staring into the event horizon of our own ignorance. But here's the comforting part. Even in the face of mystery, the questions lead us forward. The paradox doesn't paralyze, it propels. It forces us to ask, what is information? Is it physical? Is it eternal? Can it be copied, transformed, reborn? It leads us to reconsider what we mean by reality itself. If all we know of a system is written on its edge, then where truly is the system? Are we looking in or out? And it suggests that black holes, far from being silent erasers of the cosmos, may be storytellers, not in words or light, but in structure, in logic, in the deep coherence that holds the universe together, even when we can't see it. So tonight, as we sit with this paradox, don't try to solve it. Let it rest in your thoughts like a slow ripple on a quiet pond. The answers may come, or they may not. But the question itself, that is already a gift. Let's pause for a moment. We've wandered far, through event horizons, singularities, the soft curve of space-time, and the paradoxes of information. It's been a long journey, so perhaps now is a good time to step back and consider something simpler. Not the universe, not a theory, just a shoebox. Let's imagine you're out in space, not drifting, but floating gently in orbit around a distant black hole. You have in your hands a small cardboard shoebox. Maybe it once held sneakers. Maybe you filled it with other things. A letter, a flashlight, a single photograph. It doesn't matter much. What matters is that you let go. The shoebox begins to drift. At first it looks like nothing at all. It turns slightly, a slow, weightless tumble, catching a glint of starlight on one flap. It moves forward, toward the black hole, so slowly it might seem to hover. But there's a pull, soft but unrelenting. Not a tug, not a push, but a gentle insistence from the dark. Now, as it gets closer, the shoebox begins to behave differently. The first thing you notice is the light. As it nears the event horizon, the light bouncing off the box becomes redder, not because the shoebox is changing, but because the black hole's gravity is stretching the wavelength of light itself. The box doesn't glow, no, but it begins to seem tired. Diamond-size, like an old memory fading in the mind. To you, watching from outside, the fall seems to slow down. The closer the box gets to the edge, the longer it takes to fall that final distance. Time stretches. The moment becomes syrupy. The shoebox lingers on the horizon for what feels like forever. But from the box's point of view, from its quiet cardboard perspective, it is still falling, silently, smoothly, across the line where return becomes impossible, and then it disappears. Not all at once, not like a magic trick or a vanishing puff of smoke, but piece by piece, light by light. The last reflection slides away into darkness until only the curve of gravity remains. The box is gone. So what actually happened? Physically, the shoebox was spaghettified. The gravity near the black hole isn't even. It's stronger on the side closer to the centre. That difference stretches objects into long, thin shapes. It's not a violent snap. It's more like pulling taffy. First the edges go, then the seams, then the fibres and glue. Eventually the shoebox becomes a long strand of matter, one atom wide but impossibly long. And finally even that is gone. Not destroyed exactly, just absorbed, folded into the mass of the black hole. Now let's play again. What if you threw something else, something heavier? A metal spoon, for instance, or a potato, or a ticking alarm clock. Each object would fall the same way, stretched by gravity, frozen in time from your perspective, and then consumed. The spoon would bend and elongate. The potato, with all its starchy charm, would stretch too, its molecules obeying the rules of space-time like every other object. The alarm clock, still ticking as it fell, would seem to freeze in mid-air, its tick stretching infinitely, as if the last second before impact never truly arrived. Now you might wonder, does the black hole care what you drop in? Not at all. To a black hole, mass is mass, energy is energy. Whether it's a whisper of light or an elephant, a planet or a peanut, the outcome is the same. From the outside, all that matters is the combined mass, charge and spin. This is known as the no-hair theorem. Black holes, as far as we can tell, have no hair, no distinguishing features. They don't remember the details. And yet, that can't be quite the whole story, can it? You dropped a box. It had contents. Maybe it held music, our thoughts written on paper, or even just a shoelace with a story behind it. And once it passed the horizon, all of that became part of the black hole's growing mass. But did the story vanish? Or did it imprint itself somehow on the surface? Remember the holographic principle, the idea that the black hole's surface might hold the record of everything that ever fell in. Maybe the box's contents, its shape, its history were encoded there, not readable by us, but present all the same, as if the black hole has a memory of sorts, not in words, not in images, but in the arrangement of quantum bits. So your shoebox might be gone from sight, but perhaps its fall left a mark. And here's the most curious part. If you dropped yourself in, slowly, carefully, feet first or arms open, it would feel much the same. You'd fall smoothly, cross the horizon without noticing, and be stretched gently into the fabric of the black hole's mass. But your story too would remain, not because you survived, but because information can't be destroyed. It can only be changed, hidden, folded into complexity so deep we can't yet decipher it. So the universe perhaps remembers even your shoebox, even your potato, even your old ticking clock. It just doesn't tell us how. And maybe that's okay. Maybe not every question needs an answer tonight. Sometimes it's enough to watch something fall, to know it fell, and to trust that the story it carried, however small, still lingers in the dark. We've talked about black holes at length, how they pull, how they stretch, how they whisper to the fabric of space-time and gently fold it inward. But now let's return for a moment to their imagined mirror image, the white hole. Where the black hole draws in, the white hole pushes out. Where one accepts all, the other allows nothing in. One is collapse, the other eruption. And now, softly, gently, let's imagine what might happen if the two ever met. First, understand this. We're not staging a cosmic battle, not a clash of titans in the centre of the universe. Instead, think of it as a thought experiment, a meditation on contrast. Imagine two strange entities moving toward one another, not quickly, but with patient inevitability. One growing heavier, hungrier, the other pushing outward, as though it can't bear the pressure of its own existence. What would such an encounter look like? We don't know, not really. But we can let the math whisper a little. In the equations of general relativity, a white hole is a time reversal of a black hole. If you took a film of something falling in and simply reversed it, you'd see a white hole, matter and energy exploding outward, light escaping from what would normally be the point of no return. But time, in reality, doesn't always allow such symmetry, and entropy, the measure of disorder, has a say in the matter. The universe moves toward disorder, toward heat loss, toward mixing. A white hole fights this. It reduces entropy by throwing out structured information. It resists the forward flow of time, and that makes it deeply unstable. So, if a black hole and a white hole were to approach each other in the same region of space-time, the black hole, by its nature, would likely win. Not because it's stronger, not because it tries harder, but because it plays by the universe's rules. It lets things fall, it lets entropy grow. The white hole, on the other hand, fights those rules. It demands a kind of perfection the universe rarely tolerates. The white hole would begin to release energy, matter, particles, radiation. The black hole would absorb them without protest. Each photon expelled by one would be consumed by the other. Each particle pushed outward would curve back inward. The result wouldn't be a collision, it would be a quiet, inevitable absorption. Some theories suggest that this interaction, if it could ever happen, would release gravitational waves, rippling distortions in space-time, echoes of the encounter. Not unlike those we've already observed when black holes merge, though this signal might be different in tone, frequency, or duration. But there's something else to consider. If both objects are manifestations of the same underlying geometry, if a white hole is simply the reverse face of a black hole, then perhaps they're not two separate objects at all. Maybe they are two sides of the same space-time tunnel, a wormhole with an entrance and an exit. What looks like a black hole on one side might appear as a white hole on the other. The collision, then, wouldn't be a meeting, but a rejoining. And still, no evidence of white holes has ever been found. If they exist, they remain deeply hidden or deeply brief, like soap bubbles that vanish before their shimmer is even noticed. Some physicists suggest that the Big Bang itself might have been, in essence, a white hole, a point from which all matter and energy exploded outward, a singularity not of collapse, but of creation. If that's true, then perhaps every black hole is linked not just to darkness, but to a new dawn, born somewhere else beyond our seeing. But back to our quiet scenario. You imagine them now in the void, one dense, invisible, curving light inward, the other radiant but fragile, scattering matter in all directions. They move toward each other, not to fight, but to finish a sentence started long ago. And as they merge, or collapse, or cancel, the laws of physics hum softly in the background, adjusting to accommodate what can't be sustained. In the end, the black hole remains, not triumphant, just inevitable. Because in the fabric of our universe, gravity is a patient author. It doesn't rush, it doesn't shout, but it always gets the last word. And so, the white hole, an elegant idea, a bright reversal, fades into concept. The black hole absorbs its light, its mass, its message. The structure settles, the equations sigh, and the cosmos continues in different symmetry, but perhaps in some far-off brain of space, or on the edge of a different bubble of reality, the roles are reversed, and there it is the white hole that remains, the one who refused to take, who only gave. We'll likely never see it, but we can imagine it. And sometimes, in the silence of theory, that's enough. Let's try something impossible. You wake up one morning, or rather you drift gently into a thought, and the black holes are gone. All of them. Every one. The stellar mass remnants of collapsed stars, the supermassive anchors at galactic cores, the wandering interstellar beasts, vanished, as if the universe in its sleep decided to tidy them away. And so the question arrives, not with panic, but with quiet curiosity. What happens next? Black holes are often thought of as destroyers, as endings, as dead ends in the map of space-time. But they are also, strangely and profoundly, stabilizers, especially the giants that lie at the centers of galaxies. Like cosmic knots, they help hold together the swirling arms of stars, dust, and gravity. They are the invisible weights that give a galaxy its shape, its structure, its cohesion. So if you remove them all, if every black hole were to dissolve in a moment, as if erased by some higher cosmic editor, galaxies would begin to drift, not immediately, not explosively. But over time, the loss of mass would change the orbits of nearby stars. Those closest to the galactic centers would no longer curve as tightly. The inner spirals would loosen, motion would flatten, a kind of gravitational slouch would begin, order relaxing into a wider pattern. The Milky Way, for instance, has Sagittarius A star at its core, a black hole over 4 million times the mass of our Sun. Remove that anchor and our galaxy becomes a little less precise, a little more open-ended. The stars would still move, still orbit, still glow, but the grand design would blur, just slightly, like a painting left too long in sunlight. But what about smaller black holes, the stellar ones, scattered across space like punctuation marks in the story of stellar death? These are quieter, more private objects. Their disappearance would go unnoticed by most of the universe. They are not the centers of things. They are the reminders of things that once burned. If they vanished, their absence would be mostly mathematical. The balance sheets of mass and motion would adjust slightly, but the story would continue. Yet black holes are not merely gravitational actors, they are also editors of history. Every black hole holds within it a memory of what it has absorbed. A collapsed star, a drifted cloud, a piece of light that wandered too close. If you erase the black hole, you would also erase the record. Not just the mass, but the mystery. The questions we still carry. What did it consume? What lies inside? What is it becoming? If they all vanished, we'd lose the greatest puzzles in physics, the information paradox, the nature of singularities, the structure of spacetime under extreme curvature, the clues hidden in gravitational waves, all gone, not because we solved them, but because the evidence slipped away. There is also the question of energy. If black holes simply disappeared, the energy they contained would have to go somewhere. Mass does not vanish without consequence. It must be conserved. It must be accounted for. So perhaps, in their absence, we would see a flash, a moment of transformation, matter released, light unburied, the invisible becoming momentarily visible. Would it burn? Perhaps. A supermassive black hole's energy, if suddenly liberated, could outshine galaxies. It might ripple space-time, warp nearby stars. It would be like opening a box that has held pressure for billions of years and letting it all go at once. But let's soften that picture. Let's imagine instead that their disappearance is gentle, that the mass doesn't explode but unwinds, slowly, silently, into the surrounding cosmos, like a fog rising from the ground after rain, not a flash, but a hush. Their contents, not recognizable, not retrievable, merging with the background hum of the universe. And maybe, just maybe, what was once locked behind event horizons becomes the seed of something new. We often speak of black holes as endings, but in physics, endings are almost always beginnings. Stars collapse into black holes, but those black holes shape galaxies. They regulate growth. They spin. They sing in gravitational waves. They merge and create more massive forms. They are the punctuation that gives structure to the sentence of the cosmos. So if they all vanished, something else would begin. Not because they intended it, but because absence has gravity too. Perhaps the energy released would trigger star formation. New clouds would condense, light would flicker into being where once there was silence. Perhaps new galaxies would form, not anchored, not yet stable, but full of promise. Or maybe the loss would lead to cooling, a quieting of processes that once depended on extreme energy and compression. The universe would enter a slower age, a gentler phase. No more tidal disruptions, no more luminous jets, just stars and dust and time. And maybe that's the last lullaby of the black hole, that even if it vanishes, what it held gives shape to what comes next. You see, in science, nothing is truly empty, not space, not silence, not even the places where black holes once were. There is always motion, always memory, always the soft persistence of curvature. So tonight, let yourself imagine a universe without black holes. Not because it's better or safer, but because it reminds us how much they quietly do. They are the sculptors of galaxies, the keepers of lost light, the teachers of strange truths, and even in absence their shape would linger, just as all stories do long after the book is closed. You're not falling anymore, not through space, not through theory, not through gravity's long, slow pull. You're floating now. The edges that once drew closer with every question have stopped moving. Not because they've vanished, but because you've gently passed the point where reaching matters. The edge is still there, but you're no longer pressing against it. Instead, you rest beside it, watching the boundary curve like a horizon at dusk, quiet and vast. And maybe that's what the universe has been trying to teach all along, that some answers don't arrive like solutions, they arrive like peace. We've spent hours tracing the outlines of black holes, how they're formed, what they do, what they mean. We've stretched time, bent space, dropped shoeboxes into the dark, imagined whole galaxies without their anchors. We've gone as far as math can carry us. And beyond that, we've stepped softly into theory, philosophy, and dream. But there's something deeper still, because black holes are not just astrophysical objects. They are reminders of humility, of limits, of how little we see, even in the light, and of how gently the universe asks us to wonder, not to control, not to conquer, but to listen. Think of what a black hole really is, a place where the rules you trusted begin to hesitate, where time and space no longer agree, where questions echo instead of resolve, where every answer you try to bring falls inward, not rejected, but absorbed. That's not failure. That's a kind of wisdom. Not every path is meant to lead out. Some are meant to lead in. And here, in this space of silence and thought, you begin to feel that not knowing is not emptiness. It's fullness without boundary. A recognition that your place in the universe isn't outside it, looking in but within it, shaped by it, part of its slow unfolding. You, like everything else, are made of stories the universe has told over billions of years. Hydrogen forged in stars, carbon born from burning cores, particles that once flew across space, collided, settled, and eventually learned to think. And so when we say nothing escapes a black hole, we're not speaking of despair, we're speaking of transformation. The falling never really ends. It simply becomes a different kind of being. Some physicists believe that information is stored on the surface of black holes, etched like braille into the geometry of the event horizon. If that's true, then even when light fails, memory remains. And if we too are made of information, of particles and arrangements and thought, then perhaps we're never truly lost either. Perhaps we're like messages folded into the fabric of the cosmos, whispered again in new forms when the time is right. There's comfort in that, not because we need to be remembered, but because we already are. Not because the universe owes us permanence, but because it gave us this moment, this consciousness, this breath. And black holes, those quiet curvatures in the night, don't steal that from us. They reflect it. They show us where certainty bends, and in doing so, they reveal how precious this unbent world is. How rare it is to walk on a surface, to feel the rhythm of time flow forward, to look up and see stars that haven't fallen. And maybe, just maybe, that's the real lesson. That understanding doesn't mean control. That knowledge doesn't require conclusion. That the edge of what we know isn't a cliff, but a field, quiet, open, waiting. So as you rest here, floating just outside the event horizon of thought, let your questions settle. Let your mind loosen, like a boat gently untied from its dock. There's no rush now, no need to chase the center. You're already inside the story, already part of what the universe is telling itself. You are stardust, but not scattered, shaped, and you are here, not falling anymore, just listening. The edge isn't the end. It's where meaning lingers when motion slows, and now all that remains is stillness. We've come to the quiet edge of our journey, not the end of the universe, nor the end of understanding, but a gentle pause in the long conversation between you and the cosmos. You can feel it now, can't you? That slow settling, the way thought turns lighter, drifting toward dream, the way curiosity exhales and wonder softens into peace. We've walked together across the fabric of space-time, carefully, without hurry. We've stood at the rim of black holes, peered into their endless gravity, and listened to what silence sounds like when stretched across eternity. We've watched galaxies spiral around invisible hearts and wondered what it means to disappear, not in loss, but in becoming, to dissolve, to merge, to change form and still exist. And now, You're not searching anymore. You're not reaching for an answer. You're allowing it all to drift away. The equations, the questions, the edges of knowing, like dust falling through starlight. Because this was never about solving anything. It was about feeling, about resting beside the unknown long enough to realize that you are part of it. You are not separate from the universe. You are its continuation, its breath, its echo, its reflection. The atoms that make you once shone in stars, once spun in galaxies, once trembled near the pull of black holes before finding their way into your heartbeat. You're made of collapse and rebirth, of silence and spark, of rhythm and stillness. You are stardust remembering how to fall, not as an ending, but as return. So there's nothing left to remember right now. No clocks, no questions, no distances to cross. Only the quiet pulse of existence. You, here, breathing with the same slow rhythm as the universe itself. Let it hold you. Let gravity cradle you, not as a weight, but as a gentle pull toward rest. Let darkness close around you, not as absence, but as embrace. A soft veil, not to hide, but to comfort. There is no danger in this night, no urgency. Out there, black holes still turn, galaxies still sway, and light still bends, but none of it is rushing. None of it is asking anything of you. The universe too knows how to wait, not for movement, for stillness. And now that stillness belongs to you. So rest, traveler of stars. You've wandered far, through time, through gravity, through questions older than language. You've looked into the dark and found reflection, not fear. You've listened to the silence and heard the faint hum of everything that still is. And in that quiet, the truth is simple. You are not alone. You are not small. You are the universe thinking of itself, folded into a single breath. The cosmos, dreaming in the shape of a human being. And somewhere, far beyond all this, a black hole still waits, not as an end, but as a reminder. Even the darkest places glow with mystery. Even the silence has music. Even what seems to fade is only changing form. So close your eyes now. There is nothing left to grasp. You are already held, softly, completely, in the same vast rhythm that began everything. Sleep well, little part of the infinite. The universe hums around you still.